In this video, we'll discuss the valuing of multiple cash flows, which are a series of payments either received or paid through time. We'll talk about annuities, where a fixed amount is paid or received for a finite number of periods. Perpetuities, where this fixed amount is paid or received indefinitely. And growing annuities and growing perpetuities. These have the same payment structure in terms of timing as annuities and perpetuities, only the payment amount changes. It grows at a constant rate.
Multiple cash flows refers to a stream of cash flows. So a set of cash flows you'll receive over future periods where you know the timing and you either know the amount or you will estimate the amount. What we'll talk about in this chapter is valuing those multiple cash flows. We want to value those in terms of future value. If you know you're going to receive some money at different points in the future, how much will that be worth at a terminal date? Assuming you earn interest after you receive the money up through the terminal date. And also present values. If you're going to receive this stream of cash flows, what would that be worth in terms of today's dollars? What would you be equally happy receiving today as you would be receiving that stream of cash flows? First, we'll talk about calculating future values of streams of cash flows and the steps involved with that. First, you need to decide on a terminal date. That's not listed here, but you have to know when is that last period. When are we finding a future value? So you want to draw a timeline, or what I'll do is make a table so you can visualize when the different cash flows will be received. You calculate the future value of each. So for that you need to figure out a reinvestment rate. So once you receive the money, what rate of return can you earn? You'll calculate the future value up until the terminal date, add up the future values, and then you have the future value of that multiple cash flow. So let's do a couple of examples. Say at times 1, 2, 3, and 4, you'll receive cash flows, and we'll assume you receive those at the end of every period. And then the cash flows, say you receive $100, $150, $175, and $225. And your reinvestment rate is 7%. So after you receive this money, you can invest it and earn 7% up until the terminal date. So now we need to calculate future values for each of these cash flows. So we get this money at the end of period 1. We assume our terminal date is the end of period 4. So then you can invest this for 3 periods. From the end of period 1 to the end of period 2. From the end of period 2 to the end of period 3. And from the end of period 3 to the end of period 4. So that future value would be the $100 cash flow multiplied by 1 plus that investment rate raised to the third power. So 122 and 50 cents. Now you'll notice that 3 there is the number of terminal years minus when the value is received. Here, after we receive this money, we can invest it for 2 years. So the reinvestment rate squared. So 1 plus the reinvestment rate squared. That's 4 minus 2, so it's 2 periods. So you can always do that math. If you had a terminal date in 7 years and you received something in 3 years, you'd earn interest 4 times, so 7 times 3. So here you earn interest once. And here you earn interest 0 times because you received that at the terminal date. So if you add these together, your future value of that stream of cash flows is $706.49. So we've set forth the timing when the payments are received, the amounts of the payment, we have the reinvestment rate, we know the terminal date is in 4 periods, so we assume you receive this cash flow in year 1, earn interest for 3 years. This in year 2, earn interest for 2 years, and so on. And we add those all together, and we have our total future value. And also we may want to calculate present values. This will be a more common exercise in practice because many business situations call for calculating the present values of a series of expected future cash flows. So we estimate these future cash flows, what we think the project will provide or the security will provide. We calculate a present value, and we determine whether the security is a good buy at this given price, whether we should make the investment. So present value is used often for making business decisions. Calculating present value is very similar to future value. We're going to prepare that same timeline or table that identifies the timing and size of the cash flows. Calculate present values rather than future values. Add everything up, and we have the value today. In the case for security, based on the cash flows we expected to provide, what should the security be worth today? For a project, how much money would we be equally happy receiving now compared to receiving the cash flows provided by this project? Let's go through an example with present value. So we have some project or security. We estimate some cash flows. If we want to know the value of that stream of cash flows, the present value of that stream, what it's worth today, we need to discount everything to times 0. So we're going to take this cash flow, divide it by 1 plus the 11% discount rate to the first power. The same thing here, but now we need to discount it twice to get back to times 0. We need to discount the $500 3 times. And we need to discount the $650 4 times. So we're just discounting for different periods of time. We add these together, and we have a little over $1,300. So what that tells us, we'd be equally happy receiving $1,303 now or receiving this stream of cash flows. If we're evaluating the security, we could say if this security's price is less than $1,303, it's a good deal, because that's what we think it should be worth today. If we're evaluating a project, we would say the value of all the cash flows provided by that project is a little over $1,300. We could then compare that to the amount that we would need to invest and make a decision about whether we should take on that project. That's what we'll do when we calculate net present value, which is a capital budgeting technique we'll talk about in a later chapter. Now we'll talk about annuities and perpetuities. These are special cases of multiple cash flows where cash flows follow a specific pattern. Many situations exist where businesses or individuals face either receiving or paying a constant amount for some period of time. An annuity is when you pay or receive the same amount every period for some fixed number of periods, which is the case for a home loan or a car loan. Another example of an annuity would be if you're putting money away for retirement and you're putting in a set amount year after year. And in something you hear about as a retirement tool, this is actually the name. It's named this because of how the cash flows are provided, but you can buy an annuity where you pay some fixed amount now, and in exchange you receive a certain amount every month or every year for a fixed number of years. So people will buy that as an investment security so they know that they'll have some cash flows coming in after they quit working. Here's a definition of the annuity that I mentioned. Equally spaced level cash flows over a finite number of periods. So the same amount is paid or received every period. A perpetuity is similar, but this cash flow is paid or received forever, over an infinite number of periods. There aren't many good examples of perpetuities. The best and most common example is preferred stock. We assume the level of a preferred stock dividend will stay the same and will continue forever. And with annuities, we always assume that cash flows occur at the end of the period. We can have an annuity due. That's when cash flows occur at the beginning of the period. But unless otherwise stated, we'll assume we're dealing with ordinary annuities where cash flows occur at the end of each period. We talk about these special cases of cash flow streams because they're common and they occur in practice. And also we have formulas that allow us to easily calculate the future values and present values of annuities and perpetuities. So this simplifies making calculations. We can make one calculation rather than valuing every specific cash flow and adding these together. So one thing we can do, we can just calculate the value of the annuity the way we always do, single payments, and add them together. But we can also use this equation, which lets us do it directly. So write that equation down, and we're going to work through an example in Excel to show that this equation, or using the conventional method, will give you the same value. So what we'll do here, we're calculating the present value of an annuity. We just need to make this an annuity. So now, since the same amount, the 250, is being received in every period, we have an annuity, and the annuity lasts for 4 years. This is our discount rate, I. So we'll just go ahead and set this up. I is equal to 0.11. N is the number of years, 4, that goes into the equation, and the cash flow is 250. That's received every period. So we're going to show that whether you do it this way, calculate every cash flow, or use this formula, you're going to get the same answer. When you're calculating this equation, I think it's an advantage to do it in steps. So the first step I take is I calculate this part of the equation. 1 divided by 1 plus I to the n. That's my first step I calculate. So 1 divided by 1 plus I to the 4th. Next, I calculate one minus that. Then I divide that by I, so then I have the whole thing in brackets. So it equals that divided by the discount rate. And then I'll multiply this by the cash flow. And things aren't quite working out. So what I'm looking for here is a mistake. And I found a mistake here. And the way I identified it, we know the cash flows are the same. So the present value should be decreasing as time increases. So this cash flow is certainly too high. That's because I have a 2 in there instead of a 4. So here we see, after fixing the mistake, that those things match up. So it doesn't matter how you do it, you'll arrive at the same answer. As we talked about, a home or a car loan is an example of an annuity. And we talk about these, you'll hear an amortization schedule. That shows the way the borrowed amount for a loan is paid down over the life of the loan. These are typically fixed payment loans. We'll assume that's what we're dealing with here. The loan is structured so that each month some of the payment goes to paying interest and some of the payment goes to reducing principal, and this occurs until the loan is paid off. In the beginning of the loan, a smaller portion of the payment goes to take care of the principal, and the larger portion of the payment goes to pay interest. And that's because you owe more. So if you're calculating the interest owed every period on a larger amount, you owe more interest, therefore a larger portion of your payment goes towards taking care of that interest. But you'll knock off some of the principal. The next month the interest owed will be less, so more of your payment will go towards principal. And that continues until the end. Your last payment is almost entirely principal repayment. You pay a tiny bit of interest and you're done. So what an amortization schedule shows, it shows the loan balance at the beginning and end of each period, the payment made, and how that payment is broken up. How much of that payment is principal and how much is interest. You may need to reference this table in your book. This is the amortization table for a 5-year, $10,000 loan, and the interest rate on this loan is 5%. Given these characteristics, a 5-year loan with a principal of $10,000, 5% interest, annual payments, we can calculate the payment amount such that you can pay this fixed amount every year and the loan will be paid off in 5 years. The way we'll do that, we'll use the present value of an annuity formula. So you can refer back to that equation. That's equation 6.1 in your book. And what we'll do there is we'll solve for cash flow. So we know the present value of this annuity, or the value of this loan, is $10,000. We know that, so this is PVA. We know that I equals 5%, that's your interest rate, and N, the number of years, is 5. So then we can calculate that annuity factor. The annuity factor is everything on the right side of that equation 6.1 aside from the cash flow. So again, I like to go through this in steps. The first thing we'll calculate is the 1 divided by 1 plus I to the N. So that equals 1 divided by 1 plus the 5% raised to the 5th power. We subtract that from 1, and then we divide it by I. And we get 4.329. So then the way the equation would look, it would be like this. You would have present value of the annuity equals CF multiplied by 4.32948. So if we want to solve that for cash flow, we're going to take the present value of the annuity and divide it by the 4.32. So if we do that, we get our value of 2309.75. That is given in that example 6.5. That's how you calculate the payment to a fixed payment loan. If we look at this table, we can see the beginning balance is $10,000. Over the first year, 5% or $500 interest is owed. So that's going to make up part of your first payment. If you subtract that 500 from the 2309.75 and look at column 4, that means $1,809.75 went towards principal reduction, and then column 5 reflects that. The balance is reduced by that amount. In the next period, you start with that $81.90. You owe less interest because interest is only charged on the $81.90 instead of $10,000. Therefore, a larger part of your payment goes toward the principal. So instead of $1,809, now $1,900 goes towards the principal. Your balance is again reduced. Next year, even less interest is paid, and so forth until the loan is taken care of. So as we see, a larger portion of each month's payment goes towards interest in early periods. As the loan is paid down, less interest is owed. So each period, a larger percentage of that payment goes towards reducing the principal. We also have an equation for calculating the future value of an annuity. Typically, we use this calculation when we're saving for the future. So you're putting some amount of money away every year, and you want to know how much you'll have at the end. This is a common exercise for retirement planning. So equation 6.2, it gives us that fast way of working out the future value of an annuity, so that we don't have to calculate every cash flow and then add those future values up. Let's go through an example of this. Say we have 6 periods. Each period we're going to put $10,000 away. We're saving for retirement. And we have an investment rate of 8%. So first, let's do it the old-fashioned way, calculate our future values. We know our terminal time is in 6 years. So this cash flow's future value is going to be the 10,000 multiplied by 1 plus the rate. Now here we raise it to the 5th power because we're raising it to the 6 minus 1 power. because we know if we receive this in period 1, we can invest it for 5 years. So I'm just going to go ahead and fill this equation down. Now check to make sure we're right. As we go farther into time, these values should get smaller because we're earning interest over fewer periods. So that looks good. For example, here the equation would be 10,000 multiplied by 1 plus 8% to the second power, because we can earn interest from period 4 to 5 and period 5 to 6. For our future value equation, again, calculate this in steps. The first step, 1 plus I to the n minus 1. So we have 1 plus I, that interest rate, raise that to the 6th power because we have 6 periods, and then from that we subtract 1 to get 0.587. Then we take that and we divide it by I, and we get 7.34. Now we multiply that by the cash flow. So the total future value of that annuity should be $73,359. Let's see if that matches up with our total here. And it does. So we can do this either way. This formula just makes it more simple for us. Instead of doing 6 calculations and adding them up, we can do a single calculation and arrive at the same answer. So what we would say here, if you're going to invest $10,000 a year for the next 6 years and you can earn 8% per year, at the end of 6 years you would have a little over $73,000. Now on to perpetuities. Perpetuity is like an annuity. You have that constant cash flow, the same amount every period, but this goes on for an infinite number of periods. Preferred stock is really the only great example of this. Preferred stocks are considered to pay a fixed dividend, and we assume that that dividend is going to be paid forever. And we have a special equation that allows us to calculate the present value of perpetuities, and it's a pretty easy equation. We start with our present value of an annuity equation, but we substitute infinity for n. As we raise 1 plus I to infinity, that quantity goes to infinity, and 1 over infinity equals 0. So that second term in the numerator we can just get rid of. So we're left with the cash flow multiplied by 1 divided by I, which is just equal to the cash flow divided by I. So a very simple equation for the present value of a perpetuity. And the reason we would use this present value of a perpetuity equation is to calculate the price of preferred stock, what the price should be. If preferred stock pays a dividend of $2, and we assume I, the rate of interest you could earn on something of a similar risk level to this preferred stock is 4.5%. We want to know the value. We'll just take the cash flow provided per year divided by that interest rate, and the preferred stock's value should be $44.44. I want to work through an example with the present value of a perpetuity. It's not going to be perfect because we can't create a truly infinite series here, but we'll do a large number of periods. So let's change the cash flow. We'll say it's $100. And now we have a discount rate because we're calculating present value. Let's say that's 5%. So if we just take our cash flow and divide it by our discount rate, our present value should be $2,000. So now what we're going to look at each of these cash flows individually. So we're going to discount this one time. This one will be discounted twice as we fill this equation down, and so on. So we'll do this for a very large number of periods and see what our values look like. Let's go ahead and do this for 1,000 periods. So I'm just going to hide some of these rows so we can see what we're dealing with. Okay, now let's take a sum of all these. It comes out to be $2,000. And the reason for that, at some point, we can almost ignore these cash flows that are received 1,000 periods from now. That's because they're discounted so heavily that they're just non-existent. When you get out to around 200 periods, things are very close on whether the cash flow is worth more or less than half a cent. So at some point, the cash flows received very far into the future just don't matter. We mentioned annuity dues briefly. An annuity due is when the payments associated with an annuity are either paid or received at the beginning of each period rather than at the end of each period. Because of this, each period's cash flow earns an extra period of interest. Assume you receive a year 1 cash flow and you want to know the future value of that cash flow in year 5. Instead of earning interest over 4 periods, from 1 to 2, 2 to 3, 3 to 4, and 4 to 5, you earn it over 5 periods. Because really, by receiving that payment at the beginning of period 1, it's the same as receiving it at the end of period 0. So you earn extra interest. So for an annuity due, it doesn't matter whether you're talking about a future value or a present value. The way you calculate the value of an annuity due is just calculate the value of an ordinary annuity and then multiply it by 1 plus the interest rate. That takes into account that 1 extra period of earning interest. Let's go through a couple simple examples of this. We'll just do 3 period examples. We'll do 1 future value and 1 present value. And we'll have the same, because we have annuities, we'll have the same cash flow here. And in both cases, we'll assume I equals 6%. So for the future value, for these individual payments, if we're using a regular annuity, we would earn interest here twice. We would earn interest here once. And no interest here. Now up here we will be discounting. So if we discount these back to times 0, we're going to take this amount, divide it by 1 plus the rate. Here we're going to divide by 1 plus the rate squared, because it's received 2 periods into the future. And here we're going to divide it by 1 plus the rate to the third. So we can sum these up and get our total present value of this annuity. And we can do the same thing to get the future value of the annuity. Now if this is an annuity due, we are going to take this and multiply it by 1 plus the rate, because you get the interest for 1 extra period. That's the way to think about it for future value. You earn interest for 1 additional period, That's the way to think about it down here. Up here, the way to think about it is it's discounted for one less period. So if we discount this for one less period, we would take this cash flow, we would take the present value of this cash flow. So let me make these column headings more clear. We would take this present value and we would multiply it by 1 plus F1, the interest rate. So that would cancel and we would just end up with 100. If this is received at the beginning of period 1, it's received at time 0, so we don't have to discount it at all. So here are our new values. If these are annuity dues, let's go ahead and use our annuity formulas to calculate these. So step by step, we have 1 divided by 1 plus the rate to the third. Take 1 and subtract that from it. Divide that by 6% and multiply that by the cash flow. So that matches. So then we would just multiply that by 1 plus the interest rate. So we can just take what we find with our annuity formula, multiply that by 1 plus the rate, and we'll get the right answer. We can do the same thing with our future value of an annuity formula. We take 1 plus the rate, raise it to the third, and subtract 1. We divide that by the rate, multiply that by 100, multiply that by 1 plus the rate, and we get the same answer. So you just take your annuity formulas and multiply those by 1 plus the rate. In table 6.7, it goes through and it looks at payment by payment for a 4-year annuity, how an annuity differs from an annuity due when we're calculating present values. So take a look at that. It provides a good visual explanation for how the timing of cash flows changes, and therefore how the discounting of those cash flows changes, and that influences the total present value. So far we've talked about level payments, so these don't change over the life of the cash flow stream. But we also may have cash flows that grow at a constant rate over time. In reality, cash flows can take a number of patterns. They can grow, they can shrink, they can grow exponentially, they can grow at a constant rate, they can grow irregularly. But if we have these cash flow streams that grow at a constant rate, we can again use special equations to help us come to our present or future values more quickly. We'll call these growing annuities or growing perpetuities. An example would be retirement pay from a defined benefit program. Your benefit may grow at 2 or 3% each year as an adjustment for inflation. So you're receiving a known cash flow, but it's not the same. It's growing at a fixed percentage each year. Another example of a growing annuity, a business might have a multi-year contract where they're providing products or services and they receive increased cash flows every year as the business grows. So this is a growing annuity. You're receiving these cash flows for a finite number of periods, but they're growing every period. An example here is the one I just mentioned, where the cash flows the business is receiving are increasing each year at a constant rate. And this is the equation we would use for the present value of a growing annuity, where I is the discount rate and G is the growth rate. Now note that G always has to be less than I. Otherwise, I minus G is negative when it's used in the denominator of the cash flow, and you end up with values that don't make sense. So let's look at an example of this. Let's start with a cash flow of 100. We have a discount rate, I, which is 5%, and then we have a rate G, and that's the rate at which the cash flows grow. We'll assume that is 3%. So we know our cash flows are going to grow year to year by a rate of 3%. Okay, had to make sure there to show the cents also, or else it doesn't look like you're earning the compounded interest. So we're going to discount these cash flows at the discount rate I, raised to the number of years in the future they're received. And then we add these together. So that's the total present value of that growing annuity. But now let's use the other equation, and we'll do this step by step. So the first step, I'll calculate 1 plus G divided by 1 plus I. The next step is to raise that to the nth power, which in this case is 4. And then we're going to take this away from 1. So we get 0.074. In the equation there's a little box, and for some reason the multiplication sign got kicked off there. But now we'll calculate the other side of that equation, or the first part of the left side, which is the cash flow divided by I minus G. So that's 100 divided by I minus G. So that's 5,000. Now we just take the 5,000, multiply that by this factor, and we get the same amount. So again, this is just a shortcut, so we don't have to bother with all these individual calculations. And last we have a growing perpetuity. So you have this stream of cash flows that last forever. You have a starting cash flow, and then the cash flows grow every period at that fixed rate. And this is the equation that allows us to calculate the present value of a growing perpetuity. So if this were a growing perpetuity rather than an annuity, we have 100 divided by I minus G. And we expect this to be much higher because you have this infinite stream of cash flows as opposed to just 4 cash flows. So that value would come out to be $5,000. So if you're receiving $100 to start with, the payment you're going to receive grows by 3% per year, and we assume a 5% discount rate. You'd be equally happy receiving that infinite stream of cash flows as you would receiving $5,000 now. So to sum up this video, we've done a lot. It's all dealt with multiple cash flows. So as an individual or as a business, there'll be many cases where you either pay or you receive streams of cash flows that follow patterns. Either it's a constant amount or it's an amount that grows at a constant rate. If it's an irregular set where they don't follow a specific pattern, then we just have to look at every individual cash flow, calculate a future or present value, and sum those up. But if we have specific patterns like the constant or the constantly growing, then we can use the formulas we have and value these things much easier. So make sure you get some practice working out these problems. Be careful, check yourself with both methods until you get the hang of it. And always remember, if you take a present value, it's going to be less than the cash flow. If you take a future value, it's going to be more than the cash flow. That should be your first line of defense to make sure you're getting a sensible answer.